Hello everyone, my name is Muhammad Umair Khan and today I will be presenting the study which title is Data Driven Automation in Welding Leveraging Advanced Machine Learning for Quality and Efficiency. So the content of my presentation consists of abstract of our study, introduction, related work, method and materials, results and discussion, and finally we will conclude our presentations with the conclusion. So here is the abstract of this study. In this study, we analyzed 15,000 welding observations that belong to the Huntech organization through comparative analysis of SVM, which is support vector machine, MLP, multi-layer perceptron, and decision tree algorithms. Our research establishes an effective machine learning frameworks for welding parameters optimizations. The decision tree model obtained an excellent performance with the best accuracy of 80% and perfect recall. High correlation between power and thermal aspects as high as 0.96% have been obtained. The developed framework enables systematic parameter selections and demonstrates the potential for automated decision making in industrial welding applications, contributing to improved manufacturing quality and reliability. Here is the introductions where we will discuss in the recent year, the manufacturing industry has seen a significant shift toward automation driven by the need for enhanced operational efficiency and rigorous quality control measures. Traditional welding methods often face challenges in achieving uniformity and precision, leading to defects and costly rework. So, the integration of machine learning techniques presents a compelling solution to these challenges. Research has demonstrated effectiveness of support vector machines and neural networks in predicting welding outcomes. So the decision tree algorithms offer interpretable models that can aid operators in making informed decisions. So here is we will discuss about the related works, the previous works the people have done on this in this manufacturing area. Numerous studies have explored the application of machine learning in manufacturing, focusing on various aspects of process optimizations. Machine learning based systems detected weld porosity using arc sound data from PGTAW validated through K-fault cross validations. Next one used deep learning approach using CNN's automated TIG weld quality assessment across 6 categories with high accuracy. The GMAW study used a central composite design to analyze welding arc and bead geometry images. CNN application analyzed 3000 training images to predict the effectiveness of friction stir welded joints. So here we will discuss about the methodology, as I have already discussed in the previous slide that we have used three machine learning models. First one is support vector machines, multi-layer perceptron and decision tree for the classification of welding data. So basically the datasets consist of 15,000 welding observations from Huntech organizations, and its key parameters are 2.5 meter sections, 1.6 millimeter rod, and the speed is 200 to 500 maximum and minimum, current 200 to 380 amperes, voltage 29 to 48 volts, clear operational cluster in welding speeds 200, 250, 330, 350 and 450 to 500 maximum and minimum. The dataset enables optimization of operations and predictive quality control. The dataset preprocessing, comprehensive cleaning, standardizing column names, removing extra spaces, scaling options, standard scalars, robust scalar and min-max scalar considered. Feature adjustments using power transforms and Boxcox 1P. Feature selection through mutual information classification. So here we will discuss about our workflow, like already discussed we have used three machine learning models for the classification. So each algorithm was chosen for its unique strengths. SVM for kernel transformation in complex pattern. Decision tree is chosen for its clear interpretable paths, and MLP was selected for weighted connection patterns. Models were evaluated based on heterogeneity, handling, interpretability, data irregularity, management, and scalability. Implementation included parameter optimization and comprehensive performance assessment across all models. So here we will little bit discuss about the diagram, the flow diagram, workflow diagram of this study. So which basically represent a machine learning workflow starting from data preprocessing and feature engineering, that is power calculation, heat input, to the model training and validation. The model is evaluated using metrics like precision, recall, F1 score, and accuracy with iterative feedback loops for improvement. So in our study, uh, we have implemented a decision tree models with a random seed of 42 for consistency of different experiments. The models was enhanced with pruning strategies producing the best tree structure parameters. The implementation included five-fold cross-validation to prevent overfitting and visualization tools for tree structure analysis, and the performance metric measured precision, recall, F1 score, and support concerning each category. So in the next slide, we have generated correlations between engineered features. So basically this heat map shows correlation between engineered feature. Strong positive correlation exists between power heat input, heat density, and power density, while speed power ratio has strong negative correlation with these features. Current voltage ratio has weak correlation, indicating it may provide unique value. So this is totally our the correlations of our decision tree models. So here in the results and discussions, we will discuss about the comparison of machine learning models. So support vector machines basically achieved 20% accuracy, and the recall precision was 25, recall 50, and the F1 score was 33. And MLP, uh, which achieved 60% accuracy, comparably better accuracy than SVM models, and its precisions are also uh, better than the SVM, and which is 60, and recall is around 1, and means 100%, and F1 score is 80. So the decision tree model achieved in the comparison achieved high accuracy, which is 80%, which is most high accuracy as compared to the previous two models. So the precision is 50 and recall is also 1, means 100%, and F1 score is 67. So here in the results and discussions, we will discuss about welding process decision tree, like how it decision tree works in welding process. So basically this flow chart outlines the welding process based on material thickness. After checking thickness, 22 millimeter, 30 millimeter, 36 millimeter, or 40 millimeter, specific settings, feed rate, amperage, amperage voltage are applied for the first or final round. Each thickness has tailored parameters to ensure optimal welding quality. So here is the our final slides where we will conclude our presentations. We developed an effective machine learning framework for optimizing welding process with a decision tree model showing superior predictive capability, strong correlations between power and thermal features provides valuable insights for parameter selections in industrial application. Framework enhances quality control and establishes a foundation for automated decision making in manufacturing. Systematic approach improves efficiency and reliability in industrial welding operations. So here we have concluded our presentations.